Hi friends, this video we are going to talk about matrix representation of inner product. Okay, this is the very good concept who are working in the finite element method. The same idea only we are going to implement in the finite element method. So let's see, we explain. Let alpha is a set of bases fixed in some order basis like V1, V2 and so on, Vn be a fixed order basis for vector space, some inner product space V. Then suppose you have the point X belongs to vector space V, then you can represent X equal to X1 times V1 plus X2 times V2 and so on, Xn times Vn. Here all xi are scalars. So, or you can say that the coordinate vector x alpha is using the basis that is nothing but our x1, x2 and so on, xn. Okay. Suppose you have the another element y, we can write it as y equal to, y belongs to the same vector space V, it has some inner product, so we can say that V is an inner product. Similarly, we can say y1 times v1, y2 times v2 and so on, yn times vn. Correct? Now, so similarly here also the coordinate vector of y equal to y1, y2 and so on, yn. Okay. Now we say take inner product as x comma y equal to, how you can represent in terms of coordinate vector. Okay. So that is why we can write as summation I equal to 1 to n xi times vi, comma, summation j equal to 1 to n yj times vj you can represent. So using the our inner product space, we know the first axiom is x plus y comma z equal to x comma ez plus y comma ez. That is our inner product basis. Using the first argument, this is linear. So using the fact that we can take summation outside because it's a finite sum only. So summation I equal to 1 times xi, because small xi times vi, comma, summation j equal to 1 to n yj times vj we can represent. Then another axiom is, suppose symmetry x comma y same as inner product of y comma x, because our field is a some real number, real field, then it is true. Using this property you can switch summation I equal to 1 to n summation j equal to 1 to n yj vj, xi times vi. So using the same property again I apply. Using the first argument, the inner product is always linear. So then summation I equal to 1 to n summation j equal to 1 to n, you can write it as yj times vj comma xi times va. So using the homogeneity property, you can write it as directly I equal to 1 to n summation j equal to 1 to n times xi vi comma vj times yj. Here I am doing the symmetric property, we can interchange, then I can take it xi is a homogeneity property, I take xi is out, then similarly yj is I take out. Okay, then what will become, this becomes summation I equal to 1 to n summation j equal to 1 to n xi times vi comma vj times yj. It is looks like summation I equal to 1 to n summation j equal to 1 to n. So this can be written in terms of x alpha transpose times some matrix A times y alpha. Here A is the some n by n matrix is defined as vi comma vj. Correct? So it's become the scalar. This matrix A is called the matrix A is called the matrix representation of inner product. You think any inner product, you know what is the coordinate vector the corresponding to the basis, you know that, then you can define the matrix A. Okay, it will be very helpful for we can define the inner product in the computers. Okay, so that is why this inner product in the field in the computers plays a very important role. Okay, let's see one example. A simple example, I take it. Let vectors inner product space V I taken as a P2, okay, P2 of R, define inner product as f comma g equal to integral over 0 to 1 f of x times g of x dx. Okay, so my aim is I want to find the matrix representation, so I require the some order basis. Okay, now I take the standard basis. Suppose my alpha equal to 1 x and P2 means x square. This is my basis. So this is my V1, this is my V2, this is my V3. Okay. So now I want to find the matrix representation. How I can start? Yes. First step. So any polynomial P, so any element U belongs to P2 of R. How I can define this? Must be some constant times A0 plus A1 times X plus a2 times x square. This is my u, and another element v belongs to P2R. So then v equal to b0 times b1 times x plus b2 times x square. So now the inner product is defined in the terms of integral of 0 to 1 f of x times g of x. So what is the inner product of u comma v is integral over 0 to 1 u of x times v of x dx. So what is the u of x? 0 to 1 a0 plus a1 times x plus a2 times x square times b0 plus b1 x plus b2 x square times dx. Now I multiply together. So a0 times b0 plus the x coefficients are a0 times b1 plus a1 times b0 times x. These are the x coefficient will come. What about the x square coefficients are a0 times b2 plus a1 times b1 plus b0 times a2. X square terms. Then x cube term is a1 times b2 plus a2 times b1 times x cube, and finally x power 4 terms are a2 times b2 times x power 4 times dA. If you are integrate, what you will get it? This is a0 times b0 times x. If you are applying the upper limit, it become 1. Here x squared by 2. So a0 b1 plus a1 b0 divided by 2 plus a0 b2 plus a1 b1 plus a2 b0 divided by 3 plus a1 b2 plus a2 b1 divided by 4. Finally a2 times b2 divided by 5. This is the inner product of u comma v. Now we find the matrix representation, then we find the inner product. Okay. Now what is the matrix A equal to Aij, correct? The Aij is inner product of Vi comma Vj. So what is the A11? A1 means V1 inner product of V1, that is integral over 0 to 1 times dx. It's simply you will get 1. What is A12? Inner product of V1 V2. V1 is 1 times V2 is x times dx. This is 1 by 2. A13 is inner product of 0 to 1 times x square dx. You will get the 1 by 3. So the same value only you will get A21 also A31. So clearly this matrix is symmetric because inner product of Vi, Vj is Vj and Vi both are same, because inner product is always symmetric because we consider the real scalars only. So that is why A1, A2. Then we want to find A22 inner part of 0 to 1 x times x dx, that is x square. So if integrate, you will get the 1 by 3. A23 equal to integral over 0 to 1 x times x square. So you will get 1 by 4. This same way we will get the A32, and A33 is integral over 0 to 1 x power square times x power 2 times dx equal to 1 over 5, that is our A. So what is the matrix A equal to? So it has a pattern, nice pattern. We will get 1, 1 by 2, 1 by 2, and finally we will get 1 by 3 and 1 by 3. Similarly A22 also 1 by 3. A23 is 1 by 4, here also 1 by 4 and 1 by 5. This is the matrix A. Now you look, what is the coordinate vector of U? The coordinate vector of U, alpha equal to A0, A1 and A2. And similarly, V coordinate vector of V is B0, B1, B2. Now you look, now you want to find the inner part of U comma V is U coordinate vector of U transpose times A times V, inner part of coordinate vector of V. Now you say, what is the coordinate vector of U alpha is A0, A1 and A2 times the matrix is 1, 1 by 2, 1 by 3, 1 by 2, 1 by 3, 1 by 4, 1 by 3, 1 by 4 times, 1 over 5 times B0, B1 and B2. You simply multiply. So matrix multiplication is associative. So first we do the multiplication this one, then finally we do this vector multiply. Now you will get it as a B0 plus B1 divided by 2 plus B2 divided by 3, B0 divided by 2 plus B1 divided by 3 plus B2 divided by 4. Then finally B0 divided by 3 plus B1 divided by 4 plus B2 divided by 5. So next you multiply this one is A0 plus A0 B1 divided by 2 plus A0 B2 divided by 3 plus A1 is multiplied this whole thing. So A1 times B0 divided by 2 plus A1 B1 divided by 3 plus A2 A1 times B2 divided by 4 plus A2 times this one, A2 times B0 divided by 3 plus A2 times B1 divided by 4 plus A2 times B2 divided by 5. So if your coefficients, so A0 times B0 I missed here, yes. So first system is the coefficient B0 plus 1 over 2 times A0 times B1 plus A1 times B naught. So these two terms are over. Now third terms 1 over 3 coefficients are A naught B1, so A naught B2 plus A1 times B1 plus A2 times B naught. So these two terms are over. Finally 1 over 4 times A1 times B2 plus A2 times B1. So these two terms are over. Finally we write it as A2 times B2 divided by 5. The same thing only we are achieved here also. A0 times B0. So this term is over. So 1 by 2 coefficients are A0 times B1 plus A1 times B0. So this term also over. The finally 1 by 3 coefficients are A0 B2 plus A1 B1 plus A2 B0. The same thing. So we are, looks like both are same. You look, I didn't do anything in the calculation of integration. Only to evaluate the matrix A only, I used the integration. Correct? If I know that clearly, then I can inner product of any element I can make it. You please think about, suppose I am using the basis of some simple order basis I taken. Suppose I am using the orthogonal basis, what will happen? If I use the orthogonal matrix, my inner product become diagonal matrix, correct? So that gives a very nice idea to implement in the computers. Okay, so I can usually evaluate everything. So let's think this matrix definition of inner product plays an important role, especially in the finite element method. You will construct the finite element matrix, the mass matrix and stiffness matrix. At the time, the matrix definition of inner product plays a crucial role. Please think about if you are looking the basis of orthogonal basis, what will you think? Okay, I hope in this video I literally explain about matrix representation of inner product and solve one problem. Clearly you can, any inner product you will give, you can easily find the matrix. Thank you for watching this video.